Hello, good morning, good afternoon. So we are going to continue with power flows. We have seen equation for power flows at every node, and also we have seen Newton-Raphson methods as a good method for finding numerical solution of a system of nonlinear equations. How we can apply this for power flow? Let's start assuming like we have one slack bus. The first bus, typically the slack bus, has fixed voltage magnitude and voltage angle. And we assume that all the rest of buses are PQ buses, means like we know P and Q. We know active and reactive power. Then my decision variable for this load flow or power flow will be the voltage from node 2 up to node n, both angles and magnitudes. Remember that those phasor voltage are representing the state of the system. Knowing this, so finding this solution, they will be enough for defining any power or any current in the system. I have two equations per node, active and reactive power. I just bring back here on the top how looks like the formula. I will provide a reference sheet with the equations in case you need it. Observe, this particular system is plenty of sines and cosines. You know, like sines and cosines are periodic functions, and we probably expect to have several solutions. Power flows is solved using the Newton-Raphson for general case. We start with the initial iteration and we start with the initial guess. We repeat the update of this vector of unknowns. In our case will be the phase, magnitude and angles of the voltage. At every iteration is updated with the iteration v minus the inverse of the Jacobian evaluated in the iteration v multiplied by the function at the iteration v. We repeat that until we reach some level of convergence or some level of tolerance. So let's consider we have only PQ buses. That means only V and delta are the unknowns of my system of equations. So I can write the first equation, f of node I, which is related with the active power, will be equal to 0. And this is equal to this already given formulation. This is the net injection in terms of magnitude of the voltage and phase angle of the voltage minus power generated plus power demanded. This is the injection. I can actually build another equation for reactive power at every node. Well, these two functions will be the functions that I want to solve. This will be my system of equation for every I that go from 2 to n. In total I will have 2 times n minus 2 number of equations and unknowns. These two functions actually are the one we are going to use for computing the Jacobian matrix. That functions are tedious, but we can manage to make derivative with regard to voltages and with regard to phase angles. Well, here I'm giving you the first type of equation related with the active power. The derivative with regard to the phase angle of the same node is equal to this, so you can check, it's not really difficult. Or the derivative of this function of the node I with regard to the phase angle of node j is equal to this. So you can see like this Jacobian matrix for, let's say, a system like Russia that is around 9,000 nodes. The Jacobian matrix will have 2 times 9,000 is about 18 times 18. At least we can compute what are these analytical expressions for each element of this very large matrix. Similar thing we can do for this equation with regard to active power and finding the derivative with regard to these voltages. In that sense, we can build this Jacobian. What will be not possible is the construction of the inverse matrix as an analytical function. So let's see how we can apply this small case. Let's assume we have two nodes. In one node, they have one generator, which is in here, node number 1. In the other node, they have one demand, which is in here. In node 1, I'm assuming that I'm using this like a slack. So I know that the voltage it fits. It's not a decision variable, and the phase angle also is fixed. I will fix to 0. In the second node, I know P and Q. This is P, this is Q. So I don't know what are voltage into and delta into. So this node is a PQ bus. So in total, we will have 1 and 2 variables, and I will have two equations, one related with net injection reactive power in this node and net injection reactive power in this node. Here they are my variables, and then I already give you this Y matrix, or the admittance matrix. I have a series impedance of 0.1J, so it means like the series admittance is equal to minus J10. So with that, it's simple to compute what is the Y bus. And given the analytical expression for the net injection power in node I will just start to replace values. Then I need to just use these equations to describe in terms of the phasor of the voltage what are the active and reactive power at node 2. So at node 2 it will be V2 times V1. If I'm going back, like I have no real part, there is no losses or no resistive losses, so everything is reactance in series. So that's it's equal to G times JB, and there is not real part, so this is 0. So I have only this imaginary part of this admittance matrix. So this part disappears, this part disappears. I know also like V in 1 is equal to 1 and delta in 1 is equal to 0. So V in 1 is this one is equal to 1. So you see here 2 is the active power, is this value. It's 200 megawatts, but base is 100 megawatt. This is 2 ampere unit. And I have 100 megavolt ampere reactive. This is 1 per unit. This is what I see here. Okay, you can take a minute to check every value from here to here. Well, we have this equation and this equation. I can call function related with P2 to this left part, function related with Q2 to this left part. And then I can start to build the Jacobian. I just copy and paste here again, and I can write the Jacobian. Well, you can see here is the derivative of regard P2. This is actually with regard to this function of P2 and Q2. Let's do the first element, this one, and we use this equation. The derivative of this equation with regard to delta 2, so it depends only on the sign. So I have 10 is constant, B2 is constant, and then the derivative of sine is cosine of theta 2. So this is actually what we have in here. I can do this for the other 3 elements, and then I have this analytical Jacobian matrix. That is really good because I can construct the Jacobian matrix only once. It is analytical, but I can replace values in very simple way. I need just to store this matrix in memory and then just replace values to evaluate this Jacobian matrix. This Jacobian matrix is potentially sparse. So how we start this iterative process? Well, we start with an initial guess in the iteration new equal to 0. My initial guess, let's go back to remember what are my decision variables. The first variable is theta or delta, sometimes I'm calling delta, and the second variable is v. V is in per units and it should be very close to 1. So probably the first guess that I can give is 1. For the voltage phase angle, this theta 2, theta 1 is 0, so delta 2 could be probably close to 0. It's not 0, but it should be something different of 0 to have some power transfer, but it is potentially close to 0. So I can start with 0. Actually, this has a name. This is the straightforward initialization or guess that I can give to these initial variables. For B's, for magnitudes of the voltage, giving the value of 1. For the deltas, or sometimes I call thetas, giving the value 0. This is called flat start. This is my initial guess. Replacing these theta and v into the system, this is the function, this is the Jacobian. So by replacing those values, so I will have this for the function evaluated in 0, 1. This is the Jacobian evaluated in 0, 1. Then the first iteration with Newton-Raphson is this 0, 1 minus the inverse of the Jacobian times the function evaluated into 1. This function, remember, it is these two equations, this equation and this equation. Then the next values that I'm getting here is minus 0.2 for phase angle of node 2 and 0.9 for the voltage magnitude. Once again, I'm replacing in the function, so I have new value x at iteration 1 that give me different values of those equations. The Jacobian evaluated at this value is give me also a different matrix. I can update the new estimates for the solution. By replacing, I get 0.23 negative and 0.85. And if I'm replacing this in the function, I'm getting 0.01, 0.01. This is very close to 0 already. I'm almost meeting the equations. If I do another iteration, so I have another update. This is theta 2 in the iteration 2. This is voltage in 2 for the iteration 2. This is theta 2 in the iteration 3. This is voltage 2 in the iteration 3. If you check, they are almost the same. But also, we can check when we evaluate the function, the set of constraints in x3. So we see that they are all almost meeting the quality. We are done after 3 iterations, and we can stop here. Solution of our problem is V2 equal to 0.85 ohm per unit and minus 13.52 degrees. But you can present information in radians or you can present information in degrees. Well, I already mentioned that this initialization of voltage magnitude equal to 1 and voltage phase angle equal to 0, it is called flat start. It is the best guess that we can have unless we have another point that we already know is closer to the solution. They usually work for small systems, but it's not the case for large systems. So in reality, the large systems also need to have a good starting point that allows convergence. Well, finally, I would like to show you a graph. In X, you have possible values that can take the phase angle. On Y-axis is related with V. This is with theta. So it depends on which is the initial point. So if we're starting with some flat start, like this one, we will end up in the optimal solution. We start with something which is not flat start, so we also finishing in the same solution. So all this red area is representing different initial points, but they have the same color. It means like this is the same solution of the system of equations. But you can see here like there are other colors, and the other colors are representing other type of solutions. You can see even for very small case study, we can have these problems with convergence. This is by the fact that we have a lot of sines and cosines in our formulation. One could ask, why not to reformulate this in a rectangular form? In polar form, we have cosines and sines, but in rectangular form, we have just real part and imaginary part. Then we multiply real part with imaginary part, we have some byproducts. Finally, I would like to mention what happens if we have not PQ basis, but we have PV basis. Well, if we have PV basis, we know V because it's fixed, so it's not decision. One of the options and one of the ways for doing that is just to add an additional constraint. Still keep V like a variable and then generate another equation. Just say like, well, the difference between this V and the set point is equal to 0. So at the end, this difference have to be equal to 0. So this particular V have to be equal to this set point.